Hey, can folks in the chat hear me? Thanks. Okay, so as usual, don't forget the seating survey. Upcoming deadlines, the small group activity number 4 quiz is due on Thursday. I'm sorry, not the quiz. The activity is due on Thursday. The quiz for it is due on Friday, the same time that the Newton homework for this week is due. Yesterday and the day before were identical class periods that went over the material for this week. I'm hopeful that this is going to be the last week where I have to do that. I'm hoping that I can get back to the content videos over the Thanksgiving break and get those set up for you guys. But we'll have to see how things go with that. I may, in fact, instead try to catch up on all the grading. So it's not entirely clear how that's going to work just yet. If somebody wants to put up a a poll on Piazza, actually asking that question of whether you're preferring the 1 day a week intro material rather than the content videos, and so we can see what the class is thinking about that. That might be that might help inform my decision of what I'm going to do going forward. Next week is the exam. There has been a request to move it a little bit earlier so that it's not going into the Saturday and Sunday of the break. I think at most I would want to do it, maybe release on Wednesday, due on Saturday, something like that, for people who are expecting to be able to do it on a weekend day. If that idea is objectionable to somebody, let me know and we'll talk about it. My plan is for next week to be review and answering questions and trying to do exams type problems of various kinds for the in preparation for the exam. The topics on the exam are acid bases and the last details of equilibrium, where we were doing complex equilibria, where there were coupled equilibria, and the last topic, solubility products. That was the other one. So that's so most of it's going to be on the acids and bases, and just a little bit on those other aspects. The small group activity is actually a very, very good intro to what you might expect to be seeing, because it's going through a lot of those acid-base ideas. Titrations also are a very good thing to think about for the acid-base portion, because acids titrations basically bring together all of the acid-base ideas in one little package. So it makes it an easy way to sort of organize our thoughts. Now, also, my understanding is, and somebody should correct me if I'm wrong, my understanding is that after Thanksgiving break, we're not coming back to physical classes. So it's going to be entirely remote. So what I was planning to do for that period is essentially the same thing, just where I would be here with a document camera talking through things. Because I've kind of gotten used to doing the working problems under a document camera kind of thing. If anybody has other suggestions about how to do that, I'm open to other ideas. So send some ideas via Piazza if people have some other suggestions about it. Okay, any logistical questions before we start to get to some content questions? Nothing here. Okay, so there were a lot of Piazza questions about the small group activity. Is that where people would like me to focus? I'm seeing some nods. Okay, we will do that. So I'm going to call it up in another window so that I can see what I'm doing. Let's see. Where am I? There I am. All right, so let's start at the very beginning and work our way through a little bit of this. So the first question says carbon dioxide dissolved in the blood forms carbonic acid by reacting with water. Write the standard acid reaction for carbonic acid. So for a lot of people that I have been helping in office hours, they have taken that first statement as carbon dioxide dissolves in water to form carbonic acid, and have said that must be what I'm talking about. Is this the standard acid reaction for carbonic acid? I'm seeing some shakes of the head. That's right, it is not. So let's talk about how we do write what the standard acid reaction is. The standard acid reaction is to take the acid, carbonic acid, and we react it with water. In that reaction, we have it act as a Bronsted-Lowry acid. So somebody tell me, what is a Bronsted-Lowry acid? A proton donor, exactly. So what we do now is we say, let's take carbonic acid, make it be an acid donating a proton. What's left? Well, it's going to have one less hydrogen. It's lost an H+, so if it lost a plus, it's leaving behind a minus. Okay. Where does that proton go? To the water. So the water becomes hydronium. So that is the standard acid reaction for carbonic acid. And the procedure that you follow to write the standard reaction, acid reaction, is the same for every acid. All you do is you write down the acid, you have it react with water, and you make it act as a Bronsted-Lowry acid. That's it, nothing else to it. Because this is the standard acid reaction, this is the reaction for which Ka is the equilibrium constant. So in this case, our Ka is HCO3 minus H3O plus over H2CO3. So I'm going to cordon that off there. So that's our Ka for this reaction. Okay. Any questions on this part so far? All right. The second question tells us that carbonic acid, so this substance right here, has a pKa of 6.35. Blood has an average pH of 7.40. What is the ratio of the bicarbonate ion, which concentration, to the carbonic acid concentration in blood? So the thing you should do at this point, since we're talking about something having to do with a Ka, is to look at our expression for Ka we have right here. Notice that two of these components here are ratioed just like what it's asking for, the bicarbonate to the carbonic acid. So what the question is asking for is, what is HCO3 minus to H2CO3? Well, looking at this expression, that's pretty easy to get to. It's Ka over concentration of H3O plus. How do we find the Ka? Yes? It is indeed 10 to the negative pKa. So the Ka is 10 to the negative 6.35. What is our hydronium ion concentration? Yes?
10 to the negative pH.
10 to the negative pH. 10 to the negative 7.40. So we do that calculation. So let's see, 6.35, change sign, 10 to that, divided by, open parentheses, 7.4, change sign, 10 to that, close parentheses, equals 11.2. So the key here is, as you are going through these problems, and I know it seems like there's a lot of stuff to keep track of, how do you know what to use? Write down what you think you know, okay? And so what we did in question 1 was write down the standard acid reaction, and because it's an acid reaction, we suspect there's going to be an equilibrium constant involved, so go ahead and write it down even if you don't know that you need it. Write the expression down so that you have it. And that can prompt you when you are looking at the next question and seeing, it's asking me for this ratio of concentrations. Wow, I've got something really close to that right here. So that's kind of the strategy to use as you're working your way through this. Okay. Question 3. A typical concentration of bicarbonate in the blood is 26.5 millimolar. So concentration of HCO3 minus in the blood is 26.5 millimolar. And we could write it here as millimolar, or if we want to do things in molarity all the way through, we can say times 10 to the minus 3 molar. So this is, and it now asks you, what is the concentration of carbonic acid in the blood? So it's asking, what is H2CO3? Well, do we have something now that relates these two? Right here, from the previous question. The ratio of these two is 11.2. So this is going to simply be it's going to be concentration of HCO3 minus over 11.2. And so if we take 26.5 times 10 to the minus 3, 26.5 times 10 to the minus 3 divided by 11.2, we get 2.37 times 10 to the minus 3. Is that making some sense? Everybody got that? Okay. All right, let's see. Question, when I look up the ratio online, it says 20 to 1. So when I did the calc and it didn't match up with that, I thought I was wrong. Are online sources looking at the ratio in some other way, do you think? Curious why they would be so different. So the issue is that all of these concentrations, so the pH of blood, the bicarbonate concentration, and so on, all of those have a range in the human body. I picked some of the averages that I was able to find. Other people may pick different averages, averaging it in a different way, because notice that the pH is on a log scale, which means that if you're looking at the average hydronium ion concentration instead of the average pH, that average is going to be somewhere different in the normal range. So people might have taken different values for some of these components, and so they end up with a different ratio. This is one of the reasons you have to make sure that you're not just trying to Google the answers because it's not as though there's a fixed value for these things. There's a range that it seems to be in the middle of, and reasonable people can pick different values within that range as the typical example we're going to work with. Okay. All right, our next question. We are trying to give the alkaline diet argument as generous a hearing as possible. So we are going to imagine the most severe acid load we could imagine based on diet. And the idea is we want to take a lemon, the acid from lemon juice, and dump it straight into the bloodstream. So it doesn't get diluted, it doesn't have anything happen to it over the course of digestion. We're just injecting a lemon straight into your blood. I don't recommend doing this. We are also going to make the calculation simpler by saying that we take the pH of the blood, the pH of the lemon, and we're going to assume it's all coming from a strong acid. That's not the case. It's coming from a weak acid, citric acid, but we want to have a case that we can make that is relatively easy to calculate, and so we're going to assume that it's a strong acid. The first thing we need to do is to determine if we take the lemon juice and dilute it to the volume of blood that you have in the bloodstream, what would its pH end up being? What would the concentration of the hydronium ion end up being in that dilution? So this is a relatively straightforward C1V1 equals C2V2 question. Our initial volume of the lemon is 45 milliliters. Our initial concentration of hydronium ion in the lemon is going to be 10 to the minus pH. So it's going to be 10 to the minus 2 molar. C2 is the thing we're looking for. V2, our volume of blood, is going to be 5 liters. But if we're using milliliters on this side, let's just use milliliters on the other side so to make units cancel. So 5,000 milliliters. And so our C2 becomes, let's see, 10 to the minus 2 times 45 divided by 5,000 gives us 9 times 10 to the minus 5 molar. That is our hydronium ion concentration upon dilution. And so we find our pH by taking the negative log base 10 of that. And so our pH is 4.05. Is that making some sense? How we do that? Okay. All right. We are now up to question 5, which is the one that's most people seemed to be starting to have the biggest problems with. So this is the one that we really want to try to tackle. So we are imagining adding the lemon juice analog from the previous question to 5 liters of a carbonic acid bicarbonate buffer with the same concentrations as blood. So we are modeling how this carbonic acid bicarbonate buffer works in blood, but we're isolating it from all of the other things blood does. So we're trying to isolate one thing at a time. And we're going to see what effect the lemon juice getting added has on this buffer. So we need to write down an ice table, we are told. And there's a reason I asked you to do question number 1, because that's the reaction we're going to be using. So H2CO3 plus H2O in equilibrium with HCO3 minus plus H3O plus. And you are specifically told as well to use shifted initial conditions. So I'm going to make us an ICE table that has room for a shifted initial condition line. Okay. So, do we have the initial concentration for carbonic acid? Yes, from question 3, right. So our initial carbonic acid concentration was 2.37 times 10 to the minus 3. Do we have an initial bicarbonate concentration? Yes, the chat says, from the problem statement for question 3. So I'm going to write this as 2.65 times 10 to the minus 2, so that we're doing actual scientific notation rather than kind of this bastardized version. Do we have the initial hydronium ion concentration that results from adding the lemon juice to this volume of water? Yes, we do. From the previous question, 9 times 10 to the minus 5. Okay. So that is our initial set. Now, when we make a shifted initial set, what we are trying to do is to get, for a buffer system, is we're trying to take either the hydronium or the hydroxide, whichever one you're dealing with, if you're dealing with an acid reaction or a base reaction, and you're taking that to 0, so that all of the acid or base that has been added to your system is taken up in adjusting where the carbonate is in this case. Is it in bicarbonate or is it in carbonic acid? So that means if we're taking this down to 0, what do we do to find the shifted initial bicarbonate concentration? We subtract 9 times 10 to the negative 5 from this. So here we're at times 10 to the negative 2, negative 3, negative 4. So it's going to be the digit just beyond what we have here. So if we're subtracting a 9 in that digit, that rounds to basically subtracting 1 in this digit. So this is going to become 2.64 times 10 to the minus 2. On this side, what do we do to get to our shifted initial? You add the 9, that's right. So we're taking 9 in the 10 to the minus 5 place. So this is 10 to the minus 3, 4, 5. So it's going to be adding 9 in this digit here, which is a 7. So it becomes 2.46 times 10 to the minus 3. I know people have often had trouble with this concept of the shifted initial conditions. Do we have any questions on it up to this point on this one? Okay. So, yes?
Why did you choose to shift back the H3SO plus to 0 again?
So we suspect that because it's operating as a buffer, the amount of H3O plus we're going to end up with at the end is going to be pretty small, right? And so if we start with that at 0, then if you imagine what the lines are going to look like down at the bottom here, then in these two places we're going to be able to ignore the x's and we'll have just x right here. And so that'll make the math easier when we go about it. Okay, so now our change line. And I have seen another couple of questions on Piazza with people getting confused about how do you know which side's negative, which side's positive on this. The thing to look at is as the reaction occurs, either going right or left, it cannot go any further to the left because we have a zero concentration right here. It has to go to the right, meaning that you are losing reactant and you are gaining product. Okay. Equilibrium line is just the sum of the shifted initial and the change line. So 2.46 times 10 to the minus 3 minus x, 2.64 times 10 to the minus 2 plus x, and x. A question we got last week is, okay, I get how to set up these ice tables, but then you magically come up with an equation after that. Where's that equation coming from? Well, the entire point of the ice table is that these are equilibrium concentrations that we have, so we use the equilibrium constant. The equilibrium constant for this reaction is Ka, which we have a value for, well, we can call it 10 to the negative 6.35, because I didn't actually calculate that as an intermediate value. And it has the form HCO3 minus H3O plus over H2CO3. Now, if you have trouble writing down equilibrium constants expressions from balanced chemical equations, I put an Excel spreadsheet up on Blackboard that is a way for you to practice them. Essentially, you put a random number, like between 1 and 50,000, into a particular cell, and it will generate for you a random reaction. And then it asks you to enter in what is the equilibrium constant expression for it, and it checks your answer. And if you can't figure it out, you can click on a box to display what the correct answer is. So if you are having trouble figuring out how to write equilibrium constant expressions, that is a way you can practice to your heart's content on that. Okay. We now plug in the values that we have, which are the equilibrium line down at the bottom. And the easiest thing to do here is to make the assumption that x is going to be small. So it's going to be small compared to this. It's going to be small compared to this. So we will neglect it in those two cases. We will then check afterwards to see if we were right, that it was negligible in those cases. So we have 10 to the minus 6.35 equals 2.64 times 10 to the minus 2 times x over 2.46 times 10 to the minus 3. So solving for x equals 10 to the negative 6.35 times 2.46 times 10 to the minus 3 over 2.64 times 10 to the minus 2. And we now plug that into our calculator. So 6.35, change sign, 10 to that power, times 2.46 times 10 to the negative 3, divided by 2.64 times 10 to the negative 2. And we get 4.16 times 10 to the negative 1, 2, 3, 4, 5, 6, 7, 8. So is it true, make sure that that 8 is clear, is it true that x is small compared to these two values here? Yes. does X represent? Well, it's the hydronium ion concentration. So we're well on our way to finding pH. So this is H3O plus concentration. So our pH is going to be the negative log base 10 of that value. So log base 10, our pH is 7.38. What pH did we start at? 7.4. We started at 7.4 of blood, and the buffer was good enough that it only dropped by 0.02. Okay. So the next question is asking to do the same calculation, but using the Henderson-Hasselbalch equation instead. Now, this is a very, very good time-saving calculation because when you are in the buffer region, Henderson-Hasselbalch works, and it's easier than setting up an entire ice table and going through it. So let's go through how that works here. If you have, so the Henderson-Hasselbalch equation is pH equals pKa plus the log base 10 of the conjugate base concentration over the acid concentration. So we have our pKa, which is, I'm trying to remember, 6.35. We have log base 10 of our A minus and our HA. Now let's talk about how we figure that out. We started with the A minus being this value here. But remember that we adjusted it by the hydronium ion concentration, subtracting it away. That's what we have to do here as well. Since we are adding acid, what we do is we take 2.65 times 10 to the minus 2 plus, minus 9.0 times 10 to the negative 5. What was that?
Sorry about that.
Oh, it's okay. And then in the denominator, we started with 2.37 times 10 to the minus 3, and we are adding the 9.0 times 10 to the negative 5. So what we're doing is we're saying that the acid we added reduces the amount of conjugate base and creates more of the conjugate acid by that amount. We already have the results of that sum, so 6.35 plus log base 10 of 2.64 times 10 to the minus 2 over 2.46 times 10 to the minus 3. So let's now do that. 2.64 times 10 to the negative 2 divided by 2.46 times 10 to the negative 3. Take the log base 10 of that plus 6.35, and we get 7.38 for our new pH, which is identical to what we calculated up here. And as you can see, took up a lot less paper and was in many ways a lot simpler to do. It does in fact only work when X ends up being small compared to these concentrations. How do you check that that's the case? Well, you look at this and see what's my concentration and how does it compare to the sizes of my numerator and denominator here. So this is with a pH of 7, this is saying that you have 10 to the minus 7 is the concentration, and that's going to be small compared to 10 to the minus 2 and 10 to the minus 3. Okay. Any questions on doing this using Henderson-Hasselbalch? So if you had added base instead of adding acid, how do you think you would handle Henderson-Hasselbalch? Yes?
Would you just add and subtract and flip them?
Yep, you'd flip where you add and where you subtract. So you'd subtract from the bottom and you'd add to the top. So what you do is you're assuming that the base or acid that you add reacts completely with either the A minus or the HA. So if you're adding acid, it's going to react with A minus to make more HA. If you're adding base, it's going to react with HA to pull off a proton and lead to more A minus. Okay. So I'm going to stop going through the questions at that point, but I do want to jump forward to the beginning of the phosphate buffer section and talk about that part a bit. So starting on question 12. I'm not necessarily going to go through all of them in as much detail as I did right here, but I want to talk about a few of the topics. So on question 12, we have, let's see, lost my window. We are told that phosphoric acid is triprotic, meaning that all three of its hydrogens are acidic, and we are given 3 different pKa's. So the minute this happens, the minute I get that information, I start thinking I should write down the acid reactions for these things so that I have them in front of me. Okay, so H3PO4 plus H2O is in equilibrium with H2PO4 minus plus H3O plus. H2PO4 minus plus H2O is in equilibrium with HPO4 2 minus plus H3O plus. HPO4 2 minus plus H2O is in equilibrium with PO4 3 minus plus H3O plus. Each of these is doing exactly what we did right at the beginning of class today. All you do is you take the compound, you react it with water, and you make it act like an acid, so it's donating a proton, and that tells you what the products are. Then you take that product and you do it again so that you lose the second proton, and you do it again to lose the third proton. We are told that the pKa's, so pKa1 is 2.14, pKa2 is 7.20, and pKa3 is 12.37. So I do all of this before I even read what the question's asking, just to make sure that I know that I have in front of me as much information as possible so that when I see what the question's asking, I have this to refer to. So the question here is, which deprotonation step is the most important equilibrium at the pH of blood, and why? So if we're looking at which of these is in equilibrium, what we're really doing is looking at a buffer region. And so we're looking at the Henderson-Hasselbalch equation. So we are looking at pH equals pKa plus the log base 10 of the conjugate base with the acid. Now, remember when we were doing titrations, which we just did yesterday and the day before. When we titrated a weak base, with a weak acid with a strong base, we ended up with something that looked like this. So we had our equivalence point here, which was like at 8 something. And then the half equivalence point right here was where the pH equals the pKa. And so what we're saying is that in this region right here, it's acting like a buffer. So that means that the deprotonation step that is going to be the important one is going to be the one that has the pH, that has the pKa that's closest to the pH of blood. What was our pH of blood? 7.4. Well, 2.14, 7.20, 12.37, pretty clearly it's the middle one. Okay. So that means that this is going to be an equilibrium where you're going to have, within an order of magnitude, the same amount of these two substances. But that's where most of the phosphate's going to be. There's not going to be much at all of the phosphoric acid, and there's not going to be much at all of the phosphate. It's going to mostly be dihydrogen phosphate and hydrogen phosphate. So it then asks you to write the standard acid reaction for this step. Well, we already did it. It's this one right here. It asks you to determine the ratio of those concentrations. Well, we did an example of that back in question 2, so it's going to be exactly the same approach. Determining what the, then it asks you to determine how much hydrogen phosphate and dihydrogen phosphate that you have. So let's think about this for a moment. So we're going to get to a point, and I'm not going to give you the answer to that previous question yet, but in that previous question, you found a ratio of HPO4 2- to concentration of H2PO4-, right? And this was equal to some number. You have a number for that from an earlier problem. And now you're told that the sum of all of the phosphate concentrations is equal to 1.21 millimolar. So that means that, and again, you don't necessarily need to immediately jump to this, but if it says something about the sum of all of these concentrations equals a value, let's write that down. So sum of H3PO4 plus concentration of H2PO, that's a PO4 minus, plus the concentration of HPO4 2- plus the concentration of PO4 3- equals, what's it say, 1.21 millimolar. But it also says, assume that the two species you concentrated on in the previous question are the only ones that are present at meaningful concentrations. So that means we ignore that one and we ignore that one. You now have a relationship between these two concentrations. Right? So let's just call one of them X. H2PO4-, we'll call that X. What does that mean that the other one is? HPO4 2- is going to be 1.21 millimolar minus X, just from this. You can now plug those in right here. 1.21 millimolar minus X over X, it's equal to some number. You have an equation with one variable, you solve for the variable. And then that gives you one of those two concentrations. Then you go find the second one. This is really straightforward algebra right here. This is, we don't even have anything squared at this point. when you look on to the next part, it's basically asking, the next question is saying, okay, well, we neglected these two. How good was that approximation, is what it's trying to say. Well, so how do we determine that? Well, we have an equilibrium constant for the top one. So for pKa1, our Ka1 is going to be concentration of H2PO4 minus H3O plus over H3PO4, right? You have this value. You just determined this value. You know this value from the pH. So you can solve for the one you don't know. Then, to find the last one, you do exactly the same thing on the last equation here, where you have the, so you can find the PO4 3 minus concentration. So the general idea here for these types of questions is when you're given a piece of information, write it down in a way that tells you everything you can know about it. As soon as you know that this is a polyprotic acid and it has 3 equilibrium constants associated with it, write down the reactions. You might even write over to the side what the equilibrium constant expressions are for each of them as well as you go. That just gives you more information to work with to look for the relationships you need. And when you identify, oh, I know something, maybe take a different colored marker and circle it, or a highlighter or something, and highlight it saying, I know this number. And then you see what's left, what am I missing? And that'll help you work through to try to find the information you don't know. How do we know the 1.2 minus x should go on top? So here, this comes from simply looking at what's written. We have the hydrogen phosphate here in the numerator, and we wrote over here that the hydrogen phosphate is 1.21 millimolar minus x. Here we have dihydrogen phosphate equals x, so that goes in the denominator. Now you could have picked the other one over here to be x. You could have said that the hydrogen phosphate is going to be x, and this is going to be 1.21 millimolar minus x. And that's fine, you can do that. You'll just have these flipped, but when you get your answer at the end, x means the other one, and so you'll get the answers in the reverse order. And there's nothing wrong with that. It's perfectly fine. You just have to be consistent and see what you're consistent and plug in for what you have written down. Okay, so I think that going through that should be enough to get you over most of the hurdles that are present in the small group activity. And I hope you can see as we went through that the concepts we were talking about here are exactly the concepts that we've been going over. Okay. Doesn't that change their concentrations and later the pH depending on which is which? I tried it both ways and got different answers. So if you switch which one you call X, then this will be switched. And yes, you will get a different value for X. But the value for X that you get will be the concentration of HPO4 minus rather than the concentration of H2PO4 minus. And so then to find this concentration, you have to take 1.21 minus x to get that one. So the math is such that you will get the same concentrations regardless of which way you do. It's just you've defined x differently, so x will be a different value. And if that's not what happened, then there's probably an algebra mistake somewhere along the way. Okay, any other questions on the group activity at the moment? Okay, so there were a couple of muddiest points that came up that I want to tackle a little bit. One was specific Newton question that confused some people. Says, calculate the molar solubility of PbI2 in a 0.100 molar solution of PbNO3/2. The KSP of PbI2 is 8.5 times 10 to the negative ninth. And the comment was, I figured out how to do the problem, but I'm curious what about the relevance of the lead nitrate solution. Didn't use it in the calculation. It almost seemed like it didn't matter. So this is a kind of weird question. And so I feel like it is unfortunate that Newton is asking questions that are weird in this particular way. But let's nonetheless try to see if we can figure out what it's talking about. My problem with this particular question is that molar solubility usually means the solubility in molarity of a substance in pure water. It's very strange to talk about the molar solubility of a substance in a solution that has a common ion effect already in place, because there's lead that's already present in this case. That's strange to use that word here. So, but nonetheless, my interpretation of this question is that you have a solution that you're starting off with some lead in it already from the lead nitrate. And so we want to know if we put lead iodide into it, how much more lead iodide will dissolve. Okay, so with that interpretation, what I would do is write the dissolution reaction for a lead iodide. That's a solid, so we don't do anything with it. We're starting off without any of the iodide at present, but we are starting off with 0.100 molar of the lead. The only direction this can go is this way, because we have a 0 here. So 0.100 plus x, this is going to be x. So now we have our equilibrium constant expression, which is a KSP in this case. So our KSP, which equals 8.5 times 10 to the minus 9, is going to equal our lead 2 plus concentration and our, oh, hang on, I did something wrong. Because of stoichiometry, that's a 2x, and then that's a 2x here. So we have the I minus here squared in the solubility product. So let's make the simplifying approximation that the plus x here is small compared to the 0.1, which means that this now equals 0.100 times 2x quantity squared. So if we divide through by 0.1, that's the same thing as multiplying through by 10. So we have 8.5 times 10 to the minus 8th equals 4x squared. X squared equals this divided by 4. Should be able to do that in my head, but like 8.5 divided by 4. So we have 2.1 times 10 to the minus 8th. And now we take the square root of both sides. X is E8, change sign, square root. And we get 1.4 times 10 to the minus 1, 2, 3, 4 molar. And so the molar solubility of lead iodide in a solution that already has 0.1 molar of lead is going to be 1.4 times 10 to the minus 4th molar. Does that generally make some sense? Do we see how that works? Okay. All right, the only other muddiest point that I had time to write down today was how do you distinguish a strong acid titration curve from a weak acid curve? The basic idea of a strong acid curve is that as you look at pH versus volume added, that you end up with a single sharp rise, you have flat, basically this S curve, and at the equivalence point, the pH is 7 exactly. For a weak acid case, you end up with a buffer region like this. And when you get to the equivalence point, it's a pH not equal to 7. So that would be the easiest way to tell the difference of those. And I know there were some other muddiest points up on Piazza, but those were the only ones I had time to get to. So given that, I'm happy to open the floor to questions either from the chat or from people here in person about any of the material. So I have not gotten very far in writing the exam yet. Clearly, there's going to be at least one set that's going to be about buffering something. I suspect I'm probably going to do something with the carbonic acid buffering, but in a different context than blood. So perhaps something like seawater, because that's the primary buffer in seawater. And so looking at some things like how well can seawater adjust, or why is seawater getting more acidic now that we have a larger concentration of CO2 in the atmosphere because of global climate change kinds of issues. So that would be the kind of direction I might go for those kinds of questions. I haven't actually worked them out yet. I want to make sure that they are relatively straightforward calculations and they don't make you assume that you can neglect things when you can't, that sort of thing. I want to make sure I go through all of that well. In terms of titrations, we've gone through examples in class of titrating a strong acid with a strong base, titrating a weak acid with a strong base. You could imagine doing something reverse. Maybe you are given a weak base in the beaker and you're adding a strong acid to that. And so that your titration curve would be going something like that instead, which would be the inverse of what you've seen before. And so trying to think out loud here about the kinds of things that I would be asking, which would be getting at if you're understanding why things act the way they are, rather than just regurgitating the calculations you've done before. So that would be the kind of thing I could imagine doing here. Yes?
Is there going to be like systems released?
So there's a lot of pushback against the whole systems thing, that people really hated that. So I don't, Given how close to the exam we actually are right now, I don't know that you would have a lot of time to go into looking at those systems before the exam. So I suspect I'm probably not going to do that this time. So what that means is that the information for the problem will be contained in the problem or in related problems that are like right above it. Yeah, I will try to do, and I will absolutely make sure that the information that you need is in fact there. So, but keep in mind this question we had a minute ago from chat about the ratio of bicarbonate to carbonic acid in blood. When you do a Google search on it, you get 20-1, but the calculation we did based on different numbers was 11.2. And so even if what I'm giving you is a real system, which I like giving real systems because it gives context to what you're doing, going out and trying to Google the answer for it is likely not going to work because I may have picked something in a different value in the normal range to use. So use the information you're given rather than trying to look it up. I know some teachers, some instructors, when they're doing these sorts of things, will actually make up an acid that doesn't exist. You know, give you a pKa of something. Suppose there's an acid that has this property. And Chem 111 stuff give you I'm going to give you a periodic table where all of the elements are different from what you have. And the purpose of that is to give you problems that you can't just go Google to solve. And it does get at whether you understand things or not. I appreciate doing that, and I actually have some exercises that I do for a Chem 111 style class that are like that. But doing too much of that, I think, divorces your understanding from the real world examples that we need to work with. So I try to make things as real world as I can. All right, well, I mean, we have another 8 minutes we could talk about stuff if people want to. If nobody has any questions or topics to talk about, we can certainly quit early if people would like. All right, not hearing much, so let's call it good for today. Thank you, everybody.